this computer. Okay, so it's recording now. So I'll start. Okay, I mean, we anyways have to finish it also. I mean, we have to finish because the next people will be coming. You can see the screen, right?
Yes.
Yeah. Okay, so I'll start the timer. 1 second. I have the laser pointer. So okay. Okay, so hi everyone. Welcome to the 16th Małopolska Researchers Night. So the idea here would be to help you explain these like the beautiful images which are there in the background. And what we will go through is first like a bit of idea about what these what does a space-time mean, and how, or let's say what information are these images giving us of the space-time in a way. Like if you're observing the universe, you're actually observing like the events happening in the space-time. So I'll try to go through this. So in first half of the talk, I will speak about like how space-time became sort of one by the theory of Einstein, and then Arpita will take you through what do the images actually mean, like what are we actually seeing when we are like, let's observing the universe. So from the like the first half of the talk, which would be around 15-20 minutes, it would be about how space and time, these two separate concepts, became space time. And then we will try to appreciate the fact that gravity is nothing but a bending of this space time. So this is just this part will be spoken by me. Then there's the James Webb Space Telescope, which was launched previously and now has given us very amazing images and are actually telling us more about what is there in the space time. And then the physics behind this JWST images and more about the astrophysics will be discussed by Arpita. Okay, so one of my friend has joined. Thanks, Namit. So first I will talk about, let's say, the physics which was before Einstein. So the idea is to just understand where this word space-time came into the picture. So long ago, what happened is there was this guy called Young, and he performed this experiment, which is called the Young's double slit experiment. So what he did was, Thomas Young did, he said that, light is a wave and is subject to superposition principle. So what happens is, like, if you take one wave of light and the other wave of light, it sort of adds up. So there might be regions of superposition or, let's say, destructive interference. So what I mean by that is that if you have a slit like this, and if some waves are coming through this slit, so even if you have a light wave or, let's say, a water wave also, you will see some patterns forming. So where the light or, let's say, the water waves are constructively interfering, you will see dark fringes, and where they are where they are constructively interfering, you will see bright fringes, and when they are not, you are seeing dark fringes. So his experimental achievement was to demonstrate constructive and destructive interference of light. So if you are getting confused by the image on the left, then you can actually think of as water, right? So if I do this periodic thing, like periodic disturbance in the water wave, you will see that there are these regions of destructive interference and regions of constructive interference. And this was what was actually observed from light. But now you and I can think of the question that, okay, if there are waves on the water, then okay, if light is also a wave, it is also showing this character, then where is wave traveling on? So if light is a wave, then the idea is that, what is the medium of the light? So now then, long before Einstein, people started to think about what is the medium of light. So obviously light travels to outer space. You can see the sun, you can see the stars, but outer space is kind of empty. So the question the scientists or the physicists were kind of probing is that how, or let's say, where is the light flowing? What is the medium in through which the light comes and reaches our eyes or something? So they postulated that maybe light is also traveling through something. So they named this thing as some luminous ether. So this was this hypothesized, let's say, material, which was supposed to surround everything. So ether is around you, me, Earth, sun, solar system, galaxies, everything. And the light we see is sort of traveling through this ether. So this was the idea around 1800s. And this was the idea that, okay, if the sun is rotating and if the earth is revolving around it, so everything is going through the ether, right? So this was the basic postulates of the physicists at that time. So if you have a postulate, you need to have some experimental proof in order to know whether the postulate is correct or not. So in 1887, these two guys, Michelson and Morley, they came up with this experiment where they wanted to test, okay, if there is ether, if you and I are surrounded by ether, then maybe I can detect it something. So the idea was that there is a background static ether, and then sun, earth, and other planets are sort of moving to it, moving through ether. And then the idea was that ether would affect the speed of waves or particles, right? If light is flowing from the sun to the earth, it is traveling through ether. So it might happen that it affects the speed of light. So that's the idea which was trying to be implemented. So if the light is traveling in the same direction as the earth, then it means that the speed of light is higher in the direction of the earth's rotation. Now what does this mean? So imagine you have a boat which has some velocity v, and if you have some velocity of the river, then I know that the total velocity of the boat will be nothing but the velocity of the boat. So velocity of the boat plus the velocity of the river. So this was the idea that if the earth is moving around the ether, then the speed of light would be the velocity of the light plus the velocity of the ether. So this was the idea of the Michelson-Morley experiment. And their experimental setup was something like this. So they were let's say shining light from a laser to one of the mirrors, and it was allowing some light to travel in this direction, some light to travel in this direction. And when this light used to come back, this light used to come back, they will form some interference patterns, which I showed you at the beginning. So the idea was that if if this distance and this distance is the same, then there would be sort of no interference. So this was the result which was expected, that because light is traveling different distance in both the directions, then the light will be out of phase. So what you should see over here on the screen is actually destructive interference. Because see, if the ether is flowing in this direction, where I'm pointing right now, then it would take longer time for the light to go and come back in this direction than in this perpendicular direction. So you should see a destructive interference. So this is their experiment, and this is what they were, what they wanted to sort of see. But what they actually saw, that like this amazed cat, is that they saw no interference observed. And even if you turn this experiment, you might want to say that, the ether is flowing from down to up. So, okay, you can flip the experiment and do it like this. But actually, there is no interference no interference pattern is observed, and the speed of light turns out that it is actually same in all the directions. So this was the, let's say, the problem the physicists were were facing, because they were saying that there is some ether, but now they have an experiment which is telling them that, maybe there is no ether and speed of light is same in all the directions. So this Michelson-Morley experiment is actually termed as the most famous failed experiment. Now, parallelly to what was happening, like parallelly means when people were doing Michelson-Morley experiment, what else did we know about light, right? So in 1873, James Clerk Maxwell, he was finding about the theory, like how does electricity and magnetism work, right? Electricity is like, the phone is charging, then there is also magnetic field involved. So he was trying to bring electricity and magnetism together. And when you do this, and when you figure out that, okay, light is a wave, it's an electromagnetic wave, then you can determine the speed of the light. So he determined the speed of the light as 180,000 miles per second. So this was an experimental fact which was there, that the speed of light is actually this much. And people were trying to see whether it is the same in one direction or the not, depending on whether Earth is moving through the ether. So there's a very simple question what one can ask is that, what if you run at the speed of light and observe the light? So imagine that you are surfing on the water, right? So if somebody is observing you from the sea, from the shore, let's say the beach, he will see that you on your surfboard are traveling with some speed. But for you who are the surfer, who are traveling with the speed, with the wave of the water, you will see it still because you are moving with it. So this was the thought process which was going on there. But actually, this was the thought process of a 16-year-old. So this is Einstein, and his idea was that if a younger Einstein is traveling with the speed of light, will he catch up to it? How will he see light? Like if he's moving with light, then he should see light as like something which has stopped. So this was his idea. But if light is stopping, it means that the light, then it means that it would actually violate the laws of electromagnetism, because electromagnetism states that light always travels with some speed, because electromagnetic waves are moving at the speed of light. They cannot stay still. Otherwise, how you will see the sun, or let's say you will have the electromagnetic phenomena. So now Einstein came up with his theory, and this is what we will sort of look into. So in 1905, when Einstein was actually a patent clerk, so he came up with his theory, which is the special theory of relativity, and he came up with two postulates. So remember what has happened. Michelson-Morley experiment was being done to find out the speed of light in different directions. The experiment was failing. And on the other hand, we have the electromagnetism law by Maxwell, which said that the speed of light has some value. So keeping that in mind, Einstein came up with this two postulates. It says that the laws of physics are same for all inertial observers. So inertial observers are like, if you are standing still, you are an inertial observer. If you are moving with some constant velocity, you are an inertial observer. And the idea was that the laws of physics should be the same. It actually means that, so let's try to understand this concept. So suppose you are at rest, right? You are standing on ground and you see some birds are flying by. So obviously, if this bird goes here, this bird goes here, you can calculate its velocity. And suppose that I am also running in some direction. When I am running, obviously, I can also measure the velocity of this bird. But because I am running, I will measure different velocities. That is a given because I am running, right? But the laws, but the change in the velocity would be the same. What I mean to say is that if this bird moves from here to here, and if you are at rest, you will measure some change in the velocity. If I am running and if this same bird moves from here to here, obviously I will measure different velocities, but the change in the velocity would be the same. And this change in velocity is related to something which is called force. And that is the Newton's laws of force, which says that force is directly proportional to acceleration, which is the change of velocity. So here what I'm trying to say is that the laws of physics, so this is what Einstein said, that the laws of physics would be same for all the inertial observers, for you at rest and for me moving. And then he came up with his important, like say, mind-blowing postulate, number two, is that the speed of light, it's in vacuum, is same for all the inertial observers, which means that if you are at rest and observing the speed of light, and if I am running and observing the speed of light, it will actually be the same. So if there is a light bulb and it is emitting light, if you are standing still, you will measure it as C. And if I am moving with velocity V, I will also measure it as C. So the speed of light is kind of constant. And this is obviously a sad meme that if the Flash is running and if he wants to say that I am the fastest man alive, then obviously you have to give credit to your cameraman because he's taking the picture. Or maybe he can take a selfie. But anyways, but yeah, that would be tricky. Okay, so this was the mind-blowing thing that young Einstein would actually never see a stationary light. So the question which Einstein was trying to prove, that what if he goes with the speed of light, what will he actually see? So it turns out that because the speed of light is constant for all the inertial observers, he will never see a stationary light. And this was the only way to reconcile the principle of relativity, like the laws of physics are same, with the Maxwell's equation, that the speed of light has a value. It is 180,000 miles per second, but it is the speed is same in all the directions. So this was, let's say, a conceptual leap which was taken. So okay, if this is there in theory, then what are the consequences of it? What can happen? So suppose if I am at rest, so I am standing still and I shine a torch, then I measure the speed of light, as Maxwell said, that it's 180,000 miles per second. And suppose you are moving on a train in this direction, then technically you should measure the speed of light. So because the light is moving in this direction, you are moving in this. So I should measure the difference, right? So I should measure the speed of light as this. But we know that Einstein came up with this concept that the speed of light for guy at rest and the speed of light for this guy who is moving is the same. So how can you reconcile these things? Because if the speed of light is different for the guy who is moving and the guy who is still, then it means that the Maxwell's equations would look different, right? This would contradict the first postulate. So the only way to come out of this conundrum is that the solution which was given by Einstein, that the person who is who is traveling with some speed, for that person, the time is actually running slow. So if you are moving on a train and I am at rest, so your clock is actually running slow. Obviously, this is an exaggerated example, but this is actually what sort of happens. So if there are particles which are moving very fast, let's say if there's an electron or something which is moving very fast with the speed of near to the speed of light, then for them, time appears to be slow. And this is one of the consequences what happens. So in the end, am I trying to say that observers in different motion experience time differently? Which means that, okay, if I am standing still and if you are running around, then do our clock measure different time intervals? Well, actually, there is the meme. Yeah, it's actually yes. And obviously by clock, I mean not the clock which you are wearing in hand. These are like normal analog or digital clocks. But if you have an atomic clock, which I mean is a very accurate clock, then you can actually see that the time you are measuring standing still and somebody who is moving is actually different. And then do I also mean that time is relative and it varies in different frame of references? Then actually, yes. So these two are the fundamental leaps which one had to take. Because before Einstein, people used to think that time is an absolute quantity. If I'm standing still and if somebody is traveling in an aeroplane, obviously we know that the time is same. But if you have a very accurate clock, you will actually see that the guy who is moving in the aeroplane, because he's moving fast, time actually runs slow for that person. So this is one of the concept as the time dilation, which is known. So Einstein, with his cool specs now, has stated that there is no absolute time, hence there is actually no need for ether. So to conclude, before Einstein, all the work done by Lorentz, Poincaré, Minkowski, and the other people, space and time were actually different entities. And the idea was that there was an existence of absolute time. Speed of light was thought to be an observer dependent quantity. But after Einstein, it happened that space and time actually became one. They came on equal footing. Because if you are saying that somebody is moving with some speed, for that person, if the time is flowing slow, then space and time are no longer independent. They are sort of dependent and they are related by something called Lorentz equation, but I won't go into this. So this is kind of a love story of space and time. So space and time were brought on equal footing. There is no existence of absolute time, so time is kind of relative. And the speed of light in vacuum is same in all the frames. So this was one of the things. And I would almost end this part of the talk by saying, by actually quoting what Minkowski said. Minkowski was another great physicist. He said that henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. So, fun fact, when the Michelson Morley experiment was going on and people were observing the calculations, they knew that somehow space and time had to be intertwined. So, this is what Minkowski is suggesting. Then, obviously, it was the genius and let's say the boldness of Einstein who came up with that postulate and said that no, time flows differently for different observers. So that's why he's the genius. And now the idea is that, okay, if space-time is joined like, let's say, one rubber sheet, then can space-time bend, right? This is the idea. Space-time was separate, now they are together. Then can it sort of modify, right? So the idea of gravity is exactly the same, that when there is a massive body like Earth, me and you are not that massive, but if there is a huge massive body, then the space-time actually bends. And this is the idea of Einstein's general theory of relativity. So with this, he said that, okay, space-time is one continuum, and let's say if the sun is bending the space-time, so remember, he's right now putting out a theory, and then a theory is correct when it matches the observations. So he said that if there is an actual star behind the sun, then because the space-time is bent, light will take a longer path to reach. And this is how you see as the observed star position. So he was trying to say that, that if you try to observe the position of the star during a solar eclipse, you can actually calculate this bending angle. This was his prediction. And actually, this was actually found out that actually light bends across heavier objects. So this is the magic of Einstein's sort of gravity, is that space-time has become space and time became space-time. So that is special theory of relativity. But there is another more beautiful aspect that which is explained by gravity, that gravity is nothing but the bending of space-time. And there is something interesting thing which happens is called the gravitational lensing, which Arpita will go into it. So spoiler alert, I am not an artist. So if you ask me to draw an artistic picture, I will just, I don't know, take a pen, write some equations and try to convince that it's an art, but obviously it could be bad art. But if you look at this amazing picture by Van Gogh, right? This is the Starry Night, and it's one of the world's most beloved paintings, let's say. And the phenomena is very interesting because he uses something which is called immersive experience, right? You can see some structures over there. So you can see the underlying artistic beauty and all. So if I want to convey like what is an image of space-time, or what is the image of the universe, which is, let's say, the Van Gogh-esque equivalent of art, then I would actually say is this image, which was actually taken by the James Webb Telescope. So this is like, you are seeing the galaxies and other structures, but you are actually seeing some bending of space-time happening. And here is where I will end. And now Arpita will take you through the journey, like what do the images actually mean, and what are we actually seeing? So our telescopes are on the ground, they are on the space, they are observing structures, but what information are they giving? So I will stop and ask Arpita to continue. So I will stop share.
Okay, thank you so much, Syed. I would try to share my screen, and I guess you can see my screen now.
Yeah, I can see.
Okay, great. So as of now, Syed has given us a wonderful overview of what our general understanding of light has been from back early in the early 19th century, from Huygens to having the understanding of wave nature of light, to then subsequently in the early 20th century, we come across Einstein's photoelectric effect and understanding that it was also a particle as well. So we come across the wave particle duality. And then moving along, Einstein's understanding of gravity in itself and space-time, that led to the understanding of a space-time fabric. And now we have a third thing into the mix. Now we have matter. So the best part is now understanding that how does this light behave in the space-time when we have matter around it. And that is something that I think has been excellently done by just this one picture that we are seeing right in front of us, taken by James Webb Space Telescope. This is called SMACS 0723. It's a galaxy cluster right in the center. And to go into much more detail, I would just give you a small sort of understanding of this bending that Syed talked about earlier. So what you see here is, you can imagine, is the fabric of space-time, and a massive object like the one that you see in the center is the one that what it does to space-time is it bends it. So when you see the man throwing these sort of balls, rather than going on a straight trajectory, they try to follow the curvature that is in the fabric of space-time that exists just because of this bending that is of the massive object, because of the massive object. So accordingly, when we are looking at an image like this, you can literally see beautiful stars and star here of our own galaxy, but also these sort of spaghetti-like structure around it. For example, like this, just this one over here. And this is happening because of something called as gravitational lensing. So as I mentioned before, right in the center, there is a galaxy cluster. And now the galaxy cluster is a collection of hundreds and thousands of galaxies, a massive enough object to bend light. So what happens is that any galaxy that is behind this cluster, the light coming from it is actually bent, wrapped around it as it reaches us. And hence we see this sort of elongated picture, distorted picture of the galaxy behind the cluster. Apart from that, we are also seeing some sort of an elongated shapes over here, also a lot other information that just this one image can give us. For example, this beautiful spiral galaxy over here, and in this image, every single speck that you see is in fact a galaxy by in itself. So to go ahead and say why this is such an important feat and what JWST is doing and what it has achieved, let's go back and try to get a perspective about why we ended up with JWST in the first place. So this is a small image of the comparison between the primary mirrors of Hubble and JWST. So as you can see, the Hubble mirror is roughly about 2 meters in diameter, whereas the JWST primary mirror is about 6 meters larger. So what exactly a larger mirror does is that it has a larger collecting area, and hence you can see much more photons from the same region and much more fainter galaxies start to pop up in the image. So and also the difference between Hubble and JWST is that Hubble majorly sees invisible light, that is the light that you and I see on a daily basis, but JWST works on infrared light. And infrared is a slightly longer wavelength of light than the optical light that we see. So why is it suited and why was it chosen to operate in such frequency regime? The main idea is that for the James Webb Telescope is to study the earliest galaxies that were created right after the Big Bang. So the idea is that when the initial galaxy stars were being born, they emitted light that were extremely energetic, that we call ultraviolet light. And these are much more shorter wavelength of light. But as the universe is expanding, the short wavelength of light is also expanding along with it. And right now, as we see, as it reaches us, has been stretched all the way around to the infrared regime. So JWST's mirrors are meant of these infrared NIRCam or these instruments that are on board are just exactly meant to catch this light that was sent by the earliest galaxies. So now what information other than that can we observe? We also use this telescope to study the stellar nurseries, or the places where the stars are born for the very first time, about which I will also talk in the subsequent slides, but also to study planetary atmospheres, to study the composition of the things that the planetary systems apart from our own are composed of. So yeah, so we are trying to understand quite a lot of science and we can move along and look at a subtle comparison between Hubble and James Webb's telescope and move along to, okay, so before moving along, I just wanted to show you that this is an instrument, mid-infrared instrument called MIRI that is on board JWST. And a week ago, I was at the center where some parts of it were also produced in Astron in Netherlands. So just to give you a look of what the instrument looks like on board. And now moving along to another science image that was shown in by JWST was the Stefan's Quintet. So this is a group of a compact group of 5 galaxies. And the best part is that among them, 4 of them are interacting. And there is another galaxy which is more or less an imposter. So this galaxy that you see towards your left is actually a galaxy which was much more closer than the rest of the galaxies. But the remaining galaxies, like all the galaxies that you see over here, the remaining 4 are actually undergoing interaction. And how do we know that they are interacting? You can actually see this smearing of of the gas from this galaxy that you see as a tidal tail. And you also see this sort of a orangish golden tinge around it that shows of the shock waves that are rippled out of this galaxy as they are merging. So one of the best images to understand interacting galaxies was given by JWST, and this is important because we know that galaxies have evolved in the past by going through mergers such as these. And if we can study such a merger much up close and see the behavior of dust and gas in it would be an excellent tool for us to much more deeply understand the behavior of galaxies in general and their evolution. So as you see, this is also among the major questions that we are trying to answer. Moving along, there is also something called as these beautiful stellar nursery. This is called Karina Nebula. And the interesting part is that when you see them, this region in visible light, you actually see nothing except these dust clouds. So the cliffs and the pillars that you see here are the region of intense dust. And interestingly, just because of the infrared cameras on board, we can actually see the smaller, fainter stars that are embedded down here. And this is actually what is known as a stellar nursery. So a stellar nursery is a place where stars are born. And this is also some place where our sun was born a few billion years ago. So this was among the images which showed us, which can help us dig much more deeper into the places where star formation takes place and help us answer many questions regarding that as well. Moving along, we had another beautiful image that was called, this is a Southern Ring Nebula. And what you see here, this frothy region, is actually the dust, the gas that is being expelled by a dying star at the center. So this is the pointy structures that you see are a group of orbiting stars. Among them, one of them is the one that is dying and expelling out all the dust and the gas. More or less, the orange tinge that you see is molecular hydrogen gas, whereas the bluish region much more gives rise to the tinge that shows ionized gas in the center. So this is some structure that happens when a star goes through its last final stages and ends up its life in a planetary nebula by blowing off its outer surface. So it's very similar to how we are predicting or thinking that our sun is going to end its life as well in upcoming few billion years. Now, as we have gone through all these very interesting scientific images that were shown, early science release images of JWST, I would like to, in the last concluding slide, focus on what in the last few months, few weeks of observation that we got about new results that we have about our universe that we have been studying. So one of the interesting results is the discovery of these red spirals. So these are the galaxies that are actually not that much prominent, like not that much abundant in our nearby universe, but you see them in early universe, and that's a very big question, that how do these galaxies, these red spirals, were formed in the early universe? Apart from that, we also see that there are galaxies that have evolved by the time that's 500 million years after Big Bang. Now the question is that we know that initially the galaxy formation involves that first you have irregular shaped galaxies, and then you ultimately end up after a few 100 million years a proper galaxy with a disk-like structure is formed. But we see such galaxies much more early on, and the core or the central part of these galaxies are evolved and give a sort of resemblance to the galaxies that we see much later on after the universe was began. So these questions are really trying to be addressed, that how we see such evolved galaxies much previously than thought before. And not just that, but the presence of many complex elements. For example, oxygen has also been found, which hints that maybe the process of star formation and then the recurrent cycles of star formation might have happened much faster than we have thought before. Also, this is one of the images of probably the oldest or the farthest galaxy that we have known, probably 250 million years after Big Bang. So these are some of the exciting results that we are recently getting. And I think there are a lot more to go in the upcoming few months and maybe few years. Let's see what new science we are gathering as a result. So thank you so much for your patient hearing. Hope you learned something new and cool about SpaceTime. And please ask questions if you have. Thank you. So I think I'm unable to hear anything. I have finished it on time. Yes.
Yeah, you finished it on time. Sorry, I was muted.
Yes.
So we have to finish it on at 7 because there is some other event, so it will be happening. So yeah, if anyone has any questions,
Yeah, please.
Yeah, I'll see in chat. Unni has a question. So yeah, Unni, go ahead.
Hello, can you hear me?
Yeah, we can hear you.
Yeah.
So I'm asking, do we observe gravitational lensing in other wavelengths also?
You mean gravitational? Yeah, I mean gravitational. Yeah. Sorry.
What I'm saying is that our gravitational lensing images are mostly in optical, right?
Yeah, so this is actually infrared that we have been, the reason we are receiving it is in infrared, but because we cannot see infrared light, we have just made a false color image by attributing a longer wavelength of light, like artificially coloring it, but actually we see that in infrared, yes.
Okay. And I was wondering how it looks in radio also.
Sorry?
In radio, how it will be?
No.
Okay,
I will ask that. Yeah, maybe you can go to the next question.
Okay.
Okay, so
do we have any more questions?
I'll see in the chat somebody has.
Mm-hmm.
Why are the detected spirals red in the early universe?
Yeah, so that's a very good question. We don't know yet. So what you see, what red color symbolizes is that you do not have much. So bluer galaxies means there are a lot of young stars that are being formed, and there are a lot of star formation that is going on. But redder means there are more dust, and there are not much of a star formation activity going on. So we actually don't know that what has quenched that star formation activity that early in the universe. So that's among the questions that we'll try to answer.
There is one more in chat. Okay, possible post-merger. You can hear, Arpita?
Yeah, I can hear.
Yeah. So Tanya asked, why are the mirrors hexagonal in shape in JWST? Is there a specific reason for it?
I don't know why exactly hexagonal, but I know that since the mirror size has to be much larger, it is impossible to be carried exactly in a telescope. So it had to be folded. So we didn't have one circular structure like Hubble that we could just directly transport, but we had to make it in a way in which it was foldable. So maybe that was one of the reasons behind making it hexagonal shaped, so that it can be foldable. Yeah.
Maybe it's, I guess, related to the packing.
Yes.
Because in solid state, we used to do a question like, what is the packing fraction of a hexagonal lattice as compared to cubic lattice or something. But yeah, I mean, it's...
maybe it was the best possible configuration to be folded and shipped to by rocket. Yeah.
Cool. Okay, and just one more query, like, so if I see that very early, if there is no star formation and happening, it might happen that if let's say if the gas and the particles are getting ejected out from a galaxy sooner, then there is less star formation in that galaxy. Can that?
So that means that there has to be some process that is actually
causing this star.
Quenching. Okay. That is what I'm meaning when I'm saying quenching.
Quenching.
And the best part, and the thing is that these are spiral galaxies, yes? So they have retained more or less post-merger galaxies have a deformed morphology. Like, for example, they are bent and they have, as I showed in the merger, the Stefan squinted, they are merging. So they do not, how do you say, restore a proper structure. So if these spirals have undergone merging, then how do they still restore the spiral structure? But if not merging, then what is causing the quenching is also among the things that we are asking. Yeah.
Cool. Okay, thanks for the answers. So I think it's 6:56. So because there are 4 minutes left and then the other session has to happen. So if there is something more on the chat regarding red spirals, which JWST filter is there in the red color? Any quick thoughts?
It's NIRCam, but I don't know exactly the wavelengths. I would search and let you know. It's from
okay.
the NIRCam image. Yeah.
Okay, cool. Then let's reconvene at the 8 and hope there are more than the people which are right now. And okay, so I'll stop the recording.